My name is Kimia, and I'm honored to host this session and introduce our distinguished lecturer, Professor Markos Papageogiou. Markos Papageogiou received his diploma and the doctoral degrees in electrical engineering from the Technical University of Munich. He was a professor of automation at the Technical University of Munich for 6 years, and afterwards, since 1994, he has been a professor and director of Dynamic Systems and Simulation Laboratory at the Technical University of Crete in Greece. Markos is a live flow of IEEE and the flow of IPEC. He had several editorial activities, such as Associate Editor of Transportation Research Part C and the Chairman of the IPEC Technical Committee on Transportation Systems. His research interests include automatic control and optimization theory and application to transportation systems and water networks. He received several distinctions and awards, including IEEE Intelligent Transportation System Society Outstanding Research Award at 2007, and Outstanding Application Award at 2018, and the 2020 IEEE Transportation Technologies Award. Moreover, he's awarded 2 ERC Advanced Investigator grants. So today, Professor Papageogiou is going to provide us with an overview to the traffic control on freeways. Professor, we're eager to hear from you, and you can start your talk.
Thank you very much, Kimia, and thank you all for inviting me to this summer school, in which I understand the main topic is optimization and distributed optimization and applications. So my talk will be on a specific application, which is quite broad though, as you will see, and which concerns the control of freeway traffic. And by saying freeway traffic, I'm using the word freeway, which is the American word. The British word is motorway. So during the presentation, some slides call it freeway, some other slides call it motorway. You should consider it as a synonym. And I would suggest that we make the lecture interactive in the sense that I will be presenting, of course, but feel free to interrupt me at any time and ask questions. It's going to be more lively, and it may help also your colleagues to better understand something that maybe I went very fast through. So please don't be shy. Interrupt me when you want. You may also write on chat and it will be read to me in order to answer possible questions. And I will try to highlight as much as possible aspects in this application that are related to optimization and optimal control. Yes, I need to maximize, otherwise we have multiple. I will be maximizing sometimes and then minimizing again, because we have this bar here that I don't know how to get rid of it. So whenever it is covered, I will minimize again. Okay, let's start with an introduction. Motorways were first constructed in the 1930s, I believe, or 20s in the United States. And the original idea was that you have a facility, a traffic control infrastructure, a traffic infrastructure that allows users, vehicles to drive from A to B fast because of virtually unlimited capacity, and also without interruptions with traffic lights and so on. So the idea was that you have an infrastructure on which you can drive with your vehicle very fast. But as we know, starting the 60s, 70s, 80s, and increasingly until now, motorways look more like parking spaces than rather than high-speed traffic infrastructures. So, of course, in terms of physical transportation, we have done, as a mankind, huge advances. But I think that more advances have been done in virtual transmission of data. As you know, you can transmit virtually unlimited amounts of data around the globe virtually instantly. While in terms of physical transportation for our everyday needs, we are still lacking behind. And this is quite a shame for our human civilization, because even ants, even very simple species like ants, they seem to handle their traffic needs much more efficiently. And I came across this article a few years ago, and since then I'm always using it in presentations. If you read the title, Self-Organized Lane Formation and Optimized Traffic Flow, you think it's going to be something related to traffic control, but no, in army ants. So in fact, these two co-authors are zoologists, and they have studied the way ants move on their highways that connect a food source with their nest. So the ants have to pick the food, go to their nest, and then go back to pick again. And so they have a two-lane traffic. And on this two-lane highway, they found that the ants behave in a way that really optimizes throughput. So this is something, unfortunately, we did not yet manage to reach as humans. Now, this is a diagram that is very helpful because it provides some very basic understanding of what we are doing and how we should do it. Assume that we have a traffic network of any kind, and we have vehicles, customers approaching the traffic network, entering the traffic network. This is the demand, the external demand. And this happens at multiple origins. And we will assume that, for methodological reasons, that this demand is independent of any control actions that we may take. So this demand is given in space and time and does not change if we change the conditions in the network via traffic control. Now, these vehicles go through the network and exit according to the destinations of the vehicles. So they form exit flows and a total exit flow. Now, what is the simple fact? The simple fact is that with traffic control, we would like to reduce the total time spent by vehicles in the network. And it is obvious, and it can, of course, be rigorously proven with simple mathematics, that if the demand is external and is given and independent of what happens in the network, then the time spent by the vehicles in the network will be reduced if the exit flows are increased. So if you increase the exit flows, this means that vehicles will spend less time in the network. And this implies that if we want to judge the efficiency of a system, of infrastructure, we can look at exit flows. If there is something that hinders exit flows, this, by this fact, means that you increase the travel time in the system. If there is something like a control action that can increase the exit flows, then immediately you will decrease the travel time. So by looking at exit flows from a closed system, we can judge whether something is beneficial or less beneficial, or how beneficial, depending on the increase of exit flows. And under these lights, we can first look at simple queuing systems. Simple queuing systems like you go to the airport for checking in, and if the number of customers approaching the counters is higher than the number of employees, the capacity of the system, then of course you will have to queue. However, the capacity of such a simple queuing system, the serving capacity, is not a function of the queuing. So whether you are queuing or not, whether the queue is small or big, the employees at the counters work at the same pace, and the capacity is not in any way influenced by the queuing. And so any delay you experience in such a system depends only on the balance between demand and capacity. So this is a simple queuing system, but there are systems that are different. For example, a water system, if you have higher inflow and then you have higher level of water in the system, then you have a higher outflow. So in other words, in a water system, the queuing, the water level, influences positively the capacity. Capacity is not neutral to queuing. It increases with queuing, with congestion in a water system. What about traffic networks? Oops, let's see if I can move this. What about traffic networks? Well, in traffic networks, we don't have the case of the simple queuing system, and even less the case of the water system. So in traffic networks, if there is queuing, if there is congestion in the network, this degrades the capacity, the infrastructure. And the reasons for that, in the case of freeways, the reasons may be slightly different for different kinds of traffic networks. But in the case of freeways, the reasons for this degradation will be explained in a couple of minutes. So, what is the implication of this? The implication is that if you have a big network, freeway network, and then at some local link, due to more people temporarily entering the system, you have a higher demand than the local capacity, then you will have a local congestion, and this congestion will degrade the local capacity. But if the local capacity is degraded, then we will have an accelerated increase of congestion, and this will lead to a further capacity degradation, and this will still accelerated increase of congestion. So you have a vicious circle. You have a positive feedback here. System is degrading, and at the end, you have a generalized congestion in the network, which degrades the nominal capacity of that network. And if you go and measure how many people are actually served during congestion, how many are exiting in total, how many are entering, you will see that this is much less than the nominal capacity. Why? Because the system is degraded by the presence of congestion. And this will continue until after the peak period, the demand reduces clearly below the nominal capacity of the network. Then the congestion will be dissolved. And as an example, I give you here the Ile-de-France network around Paris. So for those who know, this is Paris downtown, the Boulevard Périphérique, and the expressway network around. And this is a snapshot that you can get online anytime. This was taken on the date you see here at the morning peak on a day without accidents or incidents, because if on the top of that you have accidents or incidents, then you have even more congestion. So you see here in this network that more than half of the network is red, meaning it is congested. And so it is degraded. I see that there are a couple of questions in the chat, but I don't want to go to the chat. Are those questions or just greetings?
No, there is no question. It's just
okay. Kimia, you watch and you interrupt me. All right.
Yeah, I will let you know when there is a question.
Yeah. So, in conclusion of what we said so far, we witness daily in virtually all freeway networks in and around metropolitan areas, motorway congestion, heavy motorway congestion. But given what we just said, this congestion is not only because we have very high demand. It is also because the infrastructure degrades. And so we have congested motorway networks, because we have a very expensive infrastructure. You know, freeways are very expensive to construct and very expensive to maintain. So we have an expensive infrastructure with a nominal capacity, which is not fully available. It is degraded, ironically, at the only time it is needed, because the only time we need the nominal capacity is during peak period. Off peak, anyhow, we don't have congestion, we don't have high demand. So at the only time we need it, we don't have it because the infrastructure is degraded. And the goal is to operate the motorway network optimally. As control engineers, consider the motorway network as a controllable system, which we can influence on purpose and in a way that will allow us to improve the situation. And so let me minimize for the time being. No, I cannot minimize. Okay. So, so in order to control, we will need, of course, control measures, control actuators, and we will talk about RAM metering. We will talk about mainly variable speed limits, driver information and guidance, and some emerging or new possibilities. And I don't need to say it here with you because you are all control engineers. It's important to stress when I'm talking to traffic engineers that when designing the control strategy, it is important to use systematic approaches like optimization, like feedback control, like various methodologies, and not just heuristics, because heuristics have several disadvantages that I do not need to expose with you. And I can also go quickly through this diagram of the basic elements of an automatic control system, which applies to any controlled system. So we have a process under control. And in order to be able to influence the behavior of this process, we usually install devices that we call actuators. And in order to have real-time information about the behavior of the process, we need sensors. And we have an idea about how we would like this process to behave. So we have some output of the process. Now, with the sensors, we can pick measurements from the process. In some cases, we may be even able to measure some not all, disturbances. Disturbances, as you know, are external variables that influence the behavior of the process, but cannot be manipulated by us. While inputs, controllable inputs, are again input variables that influence the process behavior, but can be within limits, be specified by us. So given all this information, we may go through a data processing block, which may contain estimation, prediction, whatever other things we may need. So the general goal of this is to extend and to enhance the real-time information given by the sensors. And all this real-time information is fed to the control strategy. And as you know, the control strategy is the brain of this whole system because it is the decision maker. So given the real-time information, the control strategy must decide at any time in real time by running this loop continuously, must decide about how to specify the control inputs so that the process behaves according to pre-specified goals, despite the impact of disturbances that are out of our control, that are real and influence, but are out of our control. So in our case of the freeway, the actuators are, as mentioned, RAM metering, variable speed limits, and others that we will see in the following, right? And the goal usually is to have, for example, what I mentioned earlier, the total time spent by all drivers being minimized. And such a loop obviously contains a lot of technological devices like sensors, communications, computers, actuators, which is, let's say, the technological skeleton for implementing a control system, but it also contains important methodological items like data processing, estimation, prediction, and most importantly, the control strategy, which are essentially the intelligence of the system. Because if you have the best technological process, and unfortunately we have many like this, the best technology in your traffic control system, but you don't have the best control strategy, then it may be in vain that you have all these devices, right? Of course, if you have a very smart control strategy, but you don't have all the other technological ingredients, also you cannot do something. So we need both, but the important thing is how smart can you be, your system can be, with the decisions it takes. Now, if we want to control a process, it is important to understand the characteristics, the features of the process in order to be able to really do the right actions at the right location. So a prerequisite for efficient traffic control in our case is understanding the reasons for the degradation of the infrastructure that I mentioned earlier, because if we know the reasons, then we can see whether we can counter these reasons and improve the situation. Now, the main problem with traffic is, of course, congestion. What we want to avoid is congestion. And so the first question is, where does congestion appear first and why? And the answer is easy. At bottleneck locations. There may be many bottleneck locations. Not all of them will create congestion, so some of them may be latent. But a bottleneck is a location where the capacity upstream is higher than the capacity downstream. Very simple. And if the incoming flow, traffic flow, is higher than the downstream capacity, then we say that the bottleneck is activated, that means we have a speed drop and a congestion upstream of the bottleneck location. And what is the reason for bottlenecks? Well, there are several reasons. And merging on-ramp can be a reason, because you have higher capacity upstream, which is the capacity of the mainstream, but also the capacity of the ramp, while downstream, you have just the capacity of the mainstream. So this can be a reason for a bottleneck. Geometry, like if you have a lane drop, if you have a strong grade, a sag, as we know, as you call it. If you have a strong curvature, if you have a tunnel or a bridge, you may have a bottleneck. Weaving sections. Weaving is when you have an on-ramp prior to an off-ramp, and so traffic has to cross on the mainstream, and this reduces the capacity. Or speed limits or overspilling of off-ramps. So these are all reasons why you may have bottlenecks, and if bottlenecks are activated, then you have congestion. And there are two main reasons why the infrastructure on freeways is degraded. So there are two main reasons for infrastructure degradation. And the first reason is called the capacity drop. And I will try to explain. So assume we have a bottleneck here, meaning the capacity downstream is lower than the capacity upstream. It does not need to be a lane drop bottleneck, as indicated here. It can be an on-ramp, it can be anything else we mentioned, a grade, strong grade, a curvature, whatever, a tunnel, a bridge. So here is the beginning of a lower capacity for some reason. Now, as long as we have inflow here lower than the downstream capacity, nothing happens essentially. So we have this diagram, which is the fundamental diagram. So this is flow versus density of vehicles. If the density is zero, the flow is zero, obviously. Then if the density is increasing, the flow is increasing. But then you have some capacity. This is the downstream capacity. If the inflow arriving exceeds this capacity, then, oops, you have a breakdown here. That means that the speed drops strongly and a congestion is forming with a tail that is moving upstream because the incoming flow is higher than the outgoing flow. So the congestion increases, moves backwards. And what you observe then at the head of the congestion is a drop of the flow. So as long as there is no breakdown, you may be able to reach the capacity of the downstream. But once you have the breakdown, then you observe a drop of the flow, which is probably due to the fact that vehicles have to accelerate from within the congestion, where the speed is low, to after the congestion, where the speed is high. So during low and high, they need to accelerate. And there are vehicles with low acceleration, vehicles with high acceleration, there are trucks. So this acceleration state here produces gaps between vehicles, long gaps. And these gaps are responsible for this capacity drop. So it's like the capacity all of a sudden dropped from a nominal value to a lower value due to the presence of the congestion. This is clearly a degradation of your system because there is one location which is very popular. Many people want to go through there. And all of a sudden, beyond a certain point of inflow, you lose how much? It can be 15, 20%, 10%. It may be different at different locations, but that's the order of magnitude. So you may be losing one lane, for example. So this is the capacity drop. And clearly, this is a first reason for degradation. A second reason is what we call blocking of off-ramps, or BOR. To understand or to explain these, let us follow the tail of the congestion, which is moving upstream. So when the tail of the congestion moves upstream, and in many cases on a ring road, for example, it may move for many kilometers, 10, 15, even more kilometers upstream. So it will cover off-ramps, more and more off-ramps. And every time an off-ramp is covered, the outflow of the off-ramp is reduced, because usually the percentage of drivers exiting is a fixed percentage, more or less fixed percentage of the main flow. But if the main flow reduces, because the congestion tail has covered the off-ramp, then the off-ramp flow reduces. And by what we said in the introduction, we then have a system in which we have a blocked off-ramp, not fully blocked, with reduced outflow. We have a mainstream exit that is also reduced due to the capacity drop. So we can expect that drivers will spend more time in the system because of this. And this gives us also an incentive what to do to avoid the degradation. Can we avoid capacity drop? How? Can we avoid congestion blocking off-ramps? How? These are the two ways that we need to consider in order to improve freeway traffic. There are no magic, there is no other ways. And it may be also worthwhile to observe here that the drivers, the vehicles exiting from these off-ramp or other off-ramps upstream that are covered by the congestion, they are not even bound to go through the bottleneck. So you have a bottleneck that is active, and you have increasingly many vehicles that are not going through these bottlenecks. But because the congestion extends more and more, these vehicles are also trapped in the congestion. They suffer the corresponding delays because their speed is lowering, and they contribute for an accelerated increase of the congestion and covering of more off-ramps and so on. So you understand that under these conditions, the degradation can be serious at network level, and we can encounter systems like the example of the Ile-de-France network, but we may have any other congested network. Okay, so after this introduction, I would like to very briefly go through modeling, because as you know, modeling is necessary whenever we want to control a process for various reasons. And I believe that Professor Van de Schutter has already talked about macroscopic traffic flow modeling of freeways and about the specific model MetaNet. Therefore, I will go relatively fast. So for a freeway network, we can divide it into links of different types and nodes. And as we will see very fast in the next slides, we can end up the whole network with a state space, nonlinear state space equation in discrete time as given here. So you have a state space equation with state vector x, control vector u, external disturbances, external variables d, where, as we will see, the state x comprises the densities and mean speeds for sections of the mainstream of about 500 meters. So for every section, we have 2 state variables, and also the origin Qs at the origins, at the on-ramps, for example. The control vector contains any RAM metering or variable speed limits or other controls that we may use. And the external variables are the demands, the appearing demand at origins of the network, and the turning rates at bifurcation. Now, let's start with the links, the motorway links, the most important part. So a link is homogeneous, it has no on-ramps, off-ramps, it goes, runs between 2 nodes, and a link, number M, is subdivided into segments or sections I. As mentioned, this can be 500 meters long. And for every such section, we have 2 state variables, the mean speed and the density. The density is in kilometers per hour, and the corresponding state equations, the first one is given here. This is the conservation equation. So any change of density in a section is due to entering minus exiting flow. The flow from traffic flow theory is the product. The flow at the exit of the segment is the product of density times mean speed. And the second state equation of the mean speed is a bit more complex. It is empirical, is given here. So as you see, it is a state equation. We have the speed at time k plus 1 on the left and only variables at time k on the right. And the change of the mean speed in a section from a value at time k to a different value k plus 1 is influenced by 3 terms, essentially. We will not go into the details. Let me just mention that the first term, called the relaxation term, depends mainly on the density of the same segment at the same time. And it is a term that relaxes the current mean speed towards a function of the density. And this function of the density is called the fundamental diagram. And it is what I mentioned earlier. So this is the full fundamental diagram. So this function, there may be different functions for fundamental diagram, but they all have this same typical shape of inverse U. They all have a unique maximum, which is the capacity of the segment. And this maximum flow is reached at a specific density value that is called the critical density. And anything below critical density is considered non-congested. Everything beyond is considered congested. And this is a function, a specific function that has 3 free parameters to be calibrated. The so-called free speed, that is the speed at 0 density, an exponential parameter A, and the critical density. These are the 3 parameters of this fundamental diagram. So this is the first term. The second term is a so-called convection term, well known for those who have studied fluid mechanics. It depends on the difference between the upstream segment speed and the segment I speed. And the third term is the so-called anticipation term, which depends on the downstream segment's density. So you see here the difference between the density of the downstream segment and the density of the current segment. And this term is responsible for moving the congestion upwards. Okay, then you may have origins like on-ramps, and this is a third, or let's say a third kind of state variable, the ramp Q. We call it here W, O for the origin. So every origin has an additional state variable, which is the Q, and the Q is obtained from a state equation that is again the conservation equation. The Q increases or decreases according to the appearing demand upstream of the Q, DO, minus the flow entering the mainstream. And the flow entering the mainstream can be influenced with RAM metering, with traffic lights. So you may have here, or you have here the flow entering the mainstream as the product between the capacity of this cross-section and RAM metering. So RAM metering is modeled here as a control variable, which is between 0 and 1, or between a minimum value and 1, because we don't want to utterly close any on-ramp. And 1 means that you have no RAM metering. So the flow entering is equal to the capacity. And it is important also that the capacity of entering depends also on the situation, on the density of the merging segment. Because if you have relatively free flow, then you can enter here freely. But if you have congested flow for some reason, then you cannot enter. So you may have a demand that cannot enter on the mainstream, and this can create a queue. And it is important to be able to model also this. Okay, then you can also model nodes. The most general case is like this. How are the flows, the incoming flows, distributed to outflows? This is done by pre-specified turning rates, beta. And there are some other coupling equations that are necessary here. I'm not going into details, but they don't introduce any additional dynamic equations, any additional state equations. So we have as state variables, the densities for every segment, the mean speeds for every segment, and the Qs at the origins. And if you consider all these equations that I presented briefly, then you end up with a general state equation for any freeway network. So it's easy based on this equation, and for any arbitrary freeway network to derive a large scale, of course, state equation of this form. So let's now advance with RAM metering. You can see here in the photograph how it works. This is the highway A6 in the south of Paris. So this is the Paris-bound direction. You see here a 3-lane highway, and you see here an on-ramp, and you barely see here the traffic lights. So with these traffic lights, you can control the insertion rate, the inflow rate from the on-ramp on the mainstream. So this is your control actuator. And we may ask, why RAM metering? And we can give two main answers and a few maybe less important from an operational point of view. And these answers are based on what we have understood regarding the degradation of the traffic. So assume this situation. You have an on-ramp and you have an upstream demand. And if the sum of the upstream demand and the on-ramp flow, the on-ramp demand, is higher than the downstream capacity, then you will have a breakdown and a Q. And at this point, you will have Q-con, that means the flow with capacity drop, Q congestion, right? Now, with RAM metering, what we can do, what we are doing, is to control the inflow from this on-ramp such that we never exceed the capacity of the mainstream, and we never fall much below, of course. Because look at this diagram, again, flow versus density. What we want to do at the outflow is to maintain, to operate the system at this level. That's what we want. If we are too restrictive, we may operate here, but then the outflow is again smaller. If we are too permissive with our control, then we may have congestion and capacity drop. We will work here. So if we are very permissive, or if we are very permissive or very restrictive, may end up from the traffic point of view, from the delay point of view, to the same situation. We need a tool that operates reliably, robustly the system here. And if we can do that, then we have here capacity flow. And then this situation is, of course, much better than this, because our system has capacity flow 20% higher than the congested system. So that's the first answer, to mitigate the capacity drop, because this system has eliminated the capacity drop, right? So it has eliminated the first reason of degradation at the expense of creating a queue here at the on-ramp. There's no other way, because the sum of the mainstream inflow and the demand at the on-ramp is higher than capacity by definition. So if you want to maintain capacity here, you must have a queue somewhere. And with RAM metering, the queue is at the on-ramp. And this is a second answer related to the second phenomenon we mentioned earlier. We now follow the congestion as it moves upstream and covers the first off-ramp. Even if we assume that there is no capacity drop, even if we write here Q cap and make the basic calculations, we will see that if gamma is the exit rate of vehicles, gamma percent of the upstream flow is exiting, then in this situation, we have this term here for the exit flow, which is lower than that. And if you cover many off-ramps upstream, you will have less and less off-ramp flow, right? And so with RAM metering, even if the capacity drop wouldn't be there, you improve the system just by increasing the off-ramp flows. So you increase the exit from the system, as we mentioned in the introduction. Of course, there is an important issue here, an important constraint. This Q, right, should not increase too much. Specifically, it should not increase so much that it covers the upstream urban junction, because these guys here, these vehicles are coming from somewhere. And if you decrease very much the flow towards the mainstream, then this queue may block some intersection, some junction upstream. And these may mess up the arterial traffic, which is not what you want. You don't want to optimize freeway traffic at the expense of the arterial. So in other words, this queue should be limited. Now, there may be other reasons. Of course, the route choice behavior of drivers will change, and you can try to exploit it to use reserve capacities on the parallel arterials. Also, safety will increase because you will have less congestion, but also safer merging. All these things have been measured in real implementations and are really present. Okay, how should we control? Let's start with local control. Local meaning you have a mainstream, you have an on-ramp, and you want to utilize measurements from this region to control the on-ramp flow. And there is such a controller. that has been around since the 1970s in the United States. And this goes like this. You measure the upstream flow, right? You assume that you know the downstream capacity, because the goal is what? The goal is to operate the system at capacity. So assuming that you know what is the downstream capacity, you just take the difference between the downstream capacity and the measured upstream flow to calculate the RAM flow that should enter in order to reach capacity flow at the exit. Now, this is a plausible, intuitive strategy, particularly for people without control background. But of course, in terms of control, it is not really what you want to do, because this is a feed-forward strategy. So it's very sensitive to disturbances. You are essentially blind. You want to control the downstream flow, but in this setting, you are blind regarding what happens downstream. You just measure upstream, but you don't know what happens downstream where you would like to have capacity. So it's not good, X. So in the 1980s, this alternative scheme was proposed, which goes by the acronym Alinea, and it is essentially an I-type regulator. What does this scheme do? Well, if we want to control the downstream, we need to measure the downstream. But of course, we don't measure the flow, because the same flow value as you see in the fundamental diagram can be encountered at free flow or at congested flow. So the flow value is not a clear indication of what are the traffic conditions. Therefore, we measure the density or the occupancy. Occupancy is a surrogate of density. Don't worry about that. You can think about density. So we measure the density, and the density is a clear indicator of where we stand. And so we can clearly say we have a target density. It is the density, the critical density, at which we have capacity flows. Let's target that critical density with our I-type regulator. So we measure the downstream occupancy. We have a set point, which is the critical, usually the critical occupancy, critical density. And then the I-type regulator will control the inflow such that we maintain the system near the set point that we have considered. After this was developed, it was found out that on the top of being closed loop and therefore much more robust than this kind of schemes, there is an additional advantage in this scheme, namely the fact that if you consider the fundamental diagram at the same location with the same conditions like weather conditions, road surface conditions, and so on, you may have different capacities. The capacity is a stochastic quantity. So today it may be, let's say, 2000, the flow at which you see the breakdown, and the next day it may be 2,200 when you see the drop, and so on. So there is a range of about 10% where you can see flow at the breakdown. And this means capacity is not something constant. So if you use here something constant, either you will fall in congestion if it is too high, or you will be too restrictive if you take here something small. While the critical density, which is the set point with the feedback regulator, is much more stable. So this doesn't change much, factually, based on measurements. And this is an additional advantage. Anyhow, this Alinea was, a revelation sorry, for traffic engineers, and still they were not able to understand how you can do this measure downstream to influence upstream. So they didn't have very often people did not have the understanding to understand this. They thought this is something natural, something God-given. You plan beforehand what you do after. And the feedback was not very understandable. We have seen in reviews, statements that are more than laughable because people just couldn't understand how you can do it this way. But of course, there were some field implementations in Paris and also in Amsterdam, the very first ones. And they clearly showed that this kind of system is much, much more efficient than that. And despite that, if you go to the United States, all local controllers are based on this so-called demand capacity strategy. And even in the Netherlands is the same. Everywhere else in the world, for local RAM metering, Alinea is being used. So still now, there are many locations going with the wrong approach. This is an example of real-life implementation of Alinea, this time from Glasgow, in Scotland. So you see that, of course, there is some stochastic change of the occupancy. This is the occupancy over time around the set point, which is the dashed line, right? But essentially, the Alinea keeps the occupancy near the critical occupancy, and that means near this location where the flow is optimized. And there are many other interesting issues related to such RAM metering, which we will not going to address in detail. For example, if the critical occupancy is not known, you may estimate it in real time. You need to estimate the queue length in real time because you don't want it to be increasing over the upstream junction. And if it does, then you need some ramp queue control. You need to control the queue so that it does not exceed the upstream junction. There are various metering policies like 1 car per green or platoons and so on. In case the bottleneck is not the merge area, but farther downstream, it's better to use a PI regulator, PI type regulator rather than I type. And further operational issues that are interesting, but we don't want to spend time with those. Now, we talked about local RAM metering. What is the alternative? The alternative is coordinated RAM metering. Coordinated means that you have the full information in the control center from measurements, and then you decide with a unique approach rather than locally about all RAM metering flows. So why do we need that, or do we need that? Assume we have a situation like this, where we have a motorway leading, let's say, to the city center, and in the AM peak, most people are going there. And then, without control, without RAM metering, this is, let's say, the ramp that contributes the last drop, and you have the overflow, you have the congestion. Of course, on the mainstream, you have many people who came from other upstream ramps. This is just the last ramp that contributed the excess flow, and you have the congestion that spreads backwards. Now, if we apply control, RAM metering, to every ramp locally, independent of the others, and without any restriction of the queuing, then here is what will happen. This last ramp will be controlled by its own Alinea. So Alinea will reduce the inflow here so that you have maximum throughput downstream. But of course, this will create a queue, and this queue may need to be relatively long, because in such a setting, this ramp will have all the pain, will pay all the pain, will suffer all the pain to keep the system running at capacity. So such a policy would be optimal from the total time spent point of view. But the poor drivers here, they will need to wait for the others, and this is not desirable and is not realistic, because they will not do it. They will divert probably to other ramps, and they will change their behavior. On the other hand, if we apply a linear independently, but with a queue limit, what will happen? Okay, that would be without control, and then with control, again, the first, this downstream ramp, Alinea, will be activated, will avoid the mainstream congestion for a period of time until the queue reaches the maximum admissible value. After this, essentially, this RAM metering is neutralized, because you cannot restrict more here, it would increase the queue. So the congestion will appear, will propagate, and only when it reaches the second on-ramp, that Alinea will be activated, and so on. So in other words, if you do local RAM metering, in case you have limited queue storage or strong demand over a whole motorway, you will be able to delay the onset of congestion. You will be able to reduce the extent of congestion at some level, but you cannot guarantee maximum throughput on the highway, because you still create the congestion. So in the coordinated case, what is needed is that on-ramps cooperate in some sense. So when one on-ramp becomes active, maybe the upstream on-ramps should start gathering also, holding back traffic. In other words, they should act like a super ramp with a much bigger storage, and then in this way guaranteeing that the queues will be distributed, will not affect only one on-ramp, and at the same time we have here capacity flow because we avoid congestion. So something like that would be good for coordinated RAM metering, and would actually be better than local RAM metering if we have limited storage space, which is of course always the case. So how can we coordinate? One way of coordinating is by applying nonlinear optimal control, in which we consider the limited storage capacity of on-ramps, the capacity in terms of traffic volumes for on-ramps. We may try to be equitable, that means to distribute queuing among multiple ramps, not put all the pain to one ramp. We may consider the nonlinear flow dynamics as given by the state equation, the nonlinear state equation. So in this case, the system knows everything, knows about the dynamic behavior of the process, knows about the constraints. If we also specify an appropriate objective criterion, we can have an optimal control problem in discrete time. And the objective criterion, we can consider the total time spent, which is a linear function of the state variables, specifically of the density and the origin queues, over a future horizon, time horizon. And we may also, if we want, consider some operational terms like the change from time step to time step of the RAM metering to avoid, very harsh changes, and also may penalize the queues at origins exceeding the maximum queue that is available. So this is a large-scale optimal control problem if we are talking about a large-scale network. And in fact, there is a software tool called AMOC, which solves this problem even for very large-scale networks within very small computational time in the order of 1 minute. But what is important is that optimal control, optimization more generally, when applied properly, it has an inherent intelligence in the sense, and I will try to highlight whenever we encounter something like that here, in the sense that it by solving this optimal control problem, it suggests to us measures, control measures, way of exploiting the control measures that we as experts of traffic flow wouldn't have thought if the optimization wouldn't suggest it to us. So in other words, we are solving an optimal control problem with numerical methods, right? And in the solution, we need to really try to explain why is this optimal and learn from it. So our creation, which is the software solving a problem, for example, like this or any other problem, can become a teacher for us to teach us how to intelligently control traffic or other things. And so it is like an instance of artificial intelligence. We are creating a guy, AMOC in this case, and this guy is our creation, but can teach us about how to do things well in ways that we didn't, as humans, think about before. Okay, so let's see an example. We take the ring road of Amsterdam. Let's take the ring road of Amsterdam. It is about only one direction, the counterclockwise direction is considered here. So it is 32 kilometers long. It has 21 on-ramps and 20 off-ramps. We will consider this problem here for quite a long period of 4 hours with a time step of 10 seconds. So the total number of involved variables is about 250,000, 250,000 variables involved in the optimal control problem. And in terms of traffic, as I said, 21 on-ramps, so 21 control variables in principle, but we have 17 on-ramps being urban on-ramps and 4 of them being motorways. So there are 4 motorways merging into this ring road motorway. And these are A1, A4, A8, and I believe there is one A2 here. Yes. So 4 ramps are merging motorways. These are simulation investigations for the no control case, but simulation with MetaNet having been calibrated with real data and feeding the simulation with real demands. So it is a very realistic simulation for the no control case because the model parameters have been calibrated to match pretty accurately the real situation. So what do we see here? This is the profile of the density. This is the space. We said 32 kilometers, so it is about 70 sections, segments. And this is the time, about 4 hours. And on the z-axis, we have the density in vehicles per kilometers per lane. And so whenever we have a mountain here, that means a high density, that means congestion. And if we zoom a little in this diagram, we will see that there is a bottleneck around here at the merging specifically of A1 with the mainstream. There is a bottleneck where congestion is triggered. And then there is a period with lower demand and lower congestion, then a second congestion, more strong even, is created here, also at the same location of A1. And on the other diagram, we see, again, in 3 dimensions, space-time, but now we see the ramp queues. So the space dimension is the 21 on-ramps. We are just looking at the queuing, the number of vehicles queuing on each of these 21 on-ramps over the same time. And what we see in the no control case are some huge queues, right? And if you look at where the queues are essentially at A4, which is emerging motorway. So if I come back to the infrastructure, A1 is here. This is the afternoon peak period. So in every afternoon, we have a congestion being created here. The congestion spills back all the way up to there. So more than half of the ring road is affected. Back here, you know, the congestion is going. But it is also spilling over on A4. So this congestion spills over on A4 and goes several kilometers also on A4. And we don't model A4 as a mainstream, but we model this as a non-ramp. And this is the reason why we have here a huge queue of more than 1,000 vehicles at A4. It's because of the spillover of congestion there. So this is the no control situation. And we can now play various games using AMOC, using this intelligent guy. And we have learned a lot. The things I mentioned earlier about coordination, most of them we learned, we understood by looking at what AMOC is doing and what AMOC considers as optimal handling of the situation. So let's play the first game. We assume that we apply optimal ramp metering without queue constraints. We can store at the on-ramps anything we want. Then we get an amazing 50% reduction of total time spent. That means the average travel time in this system, including the waiting at the on-ramps, is 50%, which is huge. And indeed, if we look at the resulting density, there is no congestion. If we look at the ramp queue profiles, we see what we were expecting. Essentially, there is a big queue at A1 because that's where the bottleneck is. So as we predicted or learned after this, there is, you know, a big queue created at the bottleneck location. And in this way, mainly, there are some other queues, but in this way, mainly, the congestion is avoided, the throughput is optimized, and we have 50% reduction. However, as also mentioned earlier, this could be achieved with in a much easier way if we apply a linear locally without queue constraints. We get also 47% by pure feedback at every local on-ramp. But again, we create this big queue, which is unacceptable. So, so the question now becomes, what if we limit the queues at the on-ramps? What if we tell the system, look, you have space for 30 vehicles at every on-ramp, at every urban on-ramp, not more than 30. And only the urban on-ramps. We don't control the freeways. We assume the freeways can merge uncontrollably. Why? Well, because in Europe, as far as I know, there is no country that has allowed so far to control motorway to motorway merges. In the United States, they do it with benefits. Unfortunately, in Europe. So we wanted to highlight to authorities what can be gained if they do it. So if we assume optimal control with a queue of, let's say, 30 vehicles for urban ramps, but no control of freeways, then 22% is considerable, is not small, but imagine that here we have a situation with a perfect model, assuming a perfect model and perfect demand prediction within the optimal control problem. So this is an upper limit. Anyhow, even so, we don't avoid the congestion fully. We do mitigate it, but we don't avoid it. You see here all these small queuing. It's the 30 vehicles that are applied by the optimal control in virtually all ramps. But we also have this huge queuing, which is due to spillover of this congestion. So ironically, if we have more RAM metering control, then we have less queuing and vice versa. Why? Because we improve the exploitation of the highway. Okay, now the question now is how much more space do we need to regain the 50% we had without ramp queue constraints? And indeed, if we allow for the 4 freeways to have storage space, admissible storage space of 200 vehicles on the top of the 30 vehicles of the urban ramps, then we regain the 50%. So in that case, you see again, no congestion. And you see here that respecting the 200 limit, we are able to avoid congestion. And of course, 200 vehicles is not so much because with merging freeways, you have much more space than on a small on-ramp. You have much more space on the freeway. And we are talking here about a system that serves about 20,000 vehicles per hour. So having a storage space of a few hundred meters here and there does not sound like something extremely difficult. Now, optimal control is valuable, but in practice, not every infrastructure owner will be keen to use optimal control. And in some cases, also the operators may not be so keen. You know, when you go, we can always design smart things in our computers and write papers, but when we are talking about applications, the big challenge is to go to the field and apply and see the improvements really materializing. Now, if you go to implement the system, then you have to tell the operator, look, you think you are the expert, but I have here a black box, AMOC, optimal control, which is smarter than you. And so you just follow what it tells you. Well, this is not the best way to gain, the confidence and the cooperation of the operators, because they would like to understand what the system is doing and why. And by realizing this fact, we said, okay, we do have this AMOC, but let's try to mimic its typical behavior with other means, feedback control, even some heuristics, in a way that is more comprehensible for the operators, because this might increase the chances of really implementing it in the field. And so we created a tool, Hero, which is completely feedback oriented. It doesn't have any prediction, any optimal control. And I outlined you how it works. So you have local alineas for every on-ramp, but there is a coordination on the top of that which watches what happens. So whenever an alinea, a local alinea becomes active, meaning that there may be a bottleneck here, Hero intervenes and asks, declares that alinea as a master, and starts recruiting slaves, slave alineas upstream, which start holding back vehicles to assist the downstream master. And so in this way, they act, as I mentioned earlier, as one single super ramp with bigger storage space that can help avoid congestion for a longer period until that bigger space is actually also filled up. So we have some heuristic rules with some appropriate feedback loops inside, which essentially mimic what we learned from AMOC and implemented it in Hero. And we tested this, of course, with the same example, and we could see that at least for this scenario, we could again reach 47%, which is close to the 50% we had earlier. And of course, this is more robust because Hero is purely feedback. So for Hero, you don't need any demand prediction. You don't need the model to be perfect. The model is what it is. Hero works only as a feedback. And by the time we had finished with Hero development, we had the luck to encounter some very progressive authorities from Australia, from the state of Victoria, and they were keen to test the strategy. So we did a test for 6 consecutive on-ramps, and there was a huge success in the outcome. They calculated that the expenses for the system were paid back within 11 days if you consider all the benefits to society due to less fuel consumption, less time delay, and so on. And these are field results before and after installation. So every small window here is a half day, and you see here red the congestion. It is half day over 20 kilometers every window, which is includes the 6 on-ramps. And you see just by looking at red and green that after Hero, the situation was much, much better for this highway. And meanwhile, Hero is operated in all freeways in the state of Victoria in Australia, and also in Queensland, Brisbane, which is another state, and also Perth, Western Australia, which is another state of Australia, and it is currently also being tested in Colorado in the United States, and there are other installations that may come. Wow, I took a very long time. I need to speed up strongly. So another tool is variable speed limits. You see here a photograph from the ring road in London. So what you see here are miles per hour. And we have speed limit per lane, but they are all the same. You will never display here a different speed limit for a different lane. And well, there is a history of manually changing speed limits, but the automated operation of speed limits started in Germany around 1970. Meanwhile, there are many application stretches in Germany, in many other countries, the Netherlands, United Kingdom, United States, Australia, probably also Switzerland. Variable speed limits are good for safety, and it was found that they can decrease the accidents by 20 or 30%, which is great. But the variable speed limit strategies that are applied until now in the field are very simplistic, and so you cannot expect improvement of traffic conditions. So this is just such a simplistic strategy. I will not explain the details. So they are operated until now based on simple lookup tables, aiming at improving safety, which is good, but you could do the same by improving also traffic efficiency. So in order to do that, we need to better understand the impact of variable speed limits. There were several assumptions about how particularly the fundamental diagram is changing when you apply speed limits. We did an exercise of calibration with real data from the UK, where 4 different variable speed limits were applied. No speed limit, the blue curve, which is 70 miles per hour, and then 60 miles per hour, 50 miles per hour, 40 miles per hour. And as you see here, and as one could expect, there is a shifting of the free speed, because the free speed is the tangent at the origin of the fundamental diagram, because flow is speed times density. So the slope at any, the chord joining the origin with any point of the fundamental diagram is the mean speed. So we see that with decreasing variable speed limits, we have a decreasing density, decreasing free speed. Also, the critical density, as you see, shifts to the right with decreasing variable speed limits. In this case here, we have also an increasing capacity for some variable speed limits. But when we did that also at another location, there was same effects for the free speed and the critical density, but no increase of capacity. And in other experiments for data from Australia and from Germany, we found out that there is no increase of capacity due to variable speed limits. So all we can do with variable speed limits is to change the fundamental diagram as indicated here. And if we can extrapolate, we can get, even for lower speed limits, a family of fundamental diagrams with decreasing capacity. So the question is, how can we influence favorably the traffic flow by decelerating it, by decreasing the speed? Now, to make sure, we entered the equations of variable speed limits in the MetaNet model and in the AMOC tool. And we ran the same situation as before. And we were very surprised to see that by using just variable speed limits, we got an improvement of 47%. You see here some congestion, but not really strong. No ramp queue, we don't apply ramp metering, and there is no spillback since there is no congestion. So AMOC, this intelligent guy, could specify a way to exploit a tool that decelerates traffic to improve the traffic conditions. And that was, of course, a huge question. How did it do it? Was there any bug in the system? Or how can you lower variable speed limits and increase travel time? Because that's what happens here. Travel time is decreased. And we needed to do a very thorough, elaboration of the results to understand as humans what AMOC provided spontaneously, and the answer is given here. Consider the same situation as before. We have a bottleneck, we have a lower capacity downstream than upstream. And if we have no control, we will have a congestion starting here, as we know from what we said before. So what is the variable speed limit doing? The variable speed limit is creating an creating a congestion at some distance from the bottom, few hundred meters. Why at some distance? Because if this congestion would be created at the bottleneck, we would have capacity drop and no change compared to no control. But if you create it farther upstream, then the vehicles have the time to accelerate out of the congestion and reach the bottleneck at a higher speed. And if you control the outflow of the congestion so as to have no congestion here and have maximum flow here, critical density, then you maximize the throughput. In other words, by holding back traffic on the mainstream rather than at an on-ramp, you do the same thing. You avoid congestion at the bottleneck and you avoid capacity drop. So the whole thing is about holding back traffic at the appropriate location and in the appropriate way so as to maximize the throughput at the bottleneck rather than suffering a capacity drop. And if you don't want to apply RAM metering to do it, you can do it on the mainstream. We call it mainstream traffic flow control, MTFC, by use of variable speed limits. So this is what AMOC essentially discovered, which we didn't think about before. Of course, in contrast to RAM metering, the congestion here is created on the mainstream, which means that you may cover some off-ramps. But because the congestion extent will be strongly reduced compared to no control, you will not cover many off-ramps, and also the flow in here is higher because you have a higher speed. So RAM metering in principle is better because it can avoid the blocking of off-ramps as well, fully. But as we have seen, variable speed limit is also very good. In this example, 47% of improvement. So this is what was discovered by AMOC and can be applied. We changed different conditions to let AMOC do the optimal thing when we wouldn't have variable speed limits everywhere. And we got always very good improvements, as you see here, even with much less variable speed limits. So every time AMOC was able to find a way or the proper way to reduce. And so, as mentioned, variable speed limits are used as control actuators for holding back traffic. There are two ways of holding back traffic. One is temporary and another one is permanent, but I will not go into the details of that. So based on this, we can think about more generally bottleneck throughput minimization for any kind of bottleneck, merging bottleneck of various kinds, weaving sections, sags, curves, and so on. All these are bottlenecks, as we know, and also tunnel or bridge entrances. All these can be bottlenecks, and for all these, we may think about a local control that would maximize the throughput. So in all these cases, we may have a an outflow that we would like to maximize. We may have an inflow, even by multiple highways or other infrastructures. If we can control some of these entrances here, based on feedback, like we do in RAM metering, but now generalized, then we can maximize the. And control devices can be traffic lights, as in RAM metering, can be physical barriers, as in toll plaza systems, can be variable speed limits, because they can also be used to hold back traffic, or can be emerging vehicle to infrastructure technologies. While some lanes can also be free. We don't need to control everything. For example, in RAM metering, we don't control the mainstream, right? We only control the RAM. So the approach is similar to the local RAM metering. We have as a main goal to keep occupancy or number of vehicles in the merge area near a set point that is an optimal set point that maximizes the throughput. And then given these, we can apply something like PI alinea to calculate a total flow that needs to reach the bottleneck. We may then distribute the flow into sub-flows according to different entering roads. And then we translate these into control decisions. So let's see an example. For example, a toll plaza, specifically the toll plaza that connects Auckland with San Francisco, the Bay Bridge. Here we have a 15-lane highway because there are booths to pay the toll. And then after this, you have a merging area, and then you have the bridge of 5 lanes. So you have 15 lanes merging into 5 lanes. And of course, if you have a high demand, you may have congestion. And we will see a simulation, first without control. So you will see here, without control, that vehicles are moving, but due to mutual hindering, in the merge area, the outflow here is reduced by about 15%, I believe, in the simulation. So this is the no control case. Why do we have the capacity drop here? Well, one could intuitively answer simply because we have too many vehicles in the merge area. Okay, but if on the other side, I would have too few vehicles in the merge area, then I would also have a reduced outflow because I don't have enough vehicles to feed the bridge. So between too many and too few, there is probably an optimal number of vehicles that produces the maximum throughput. So we can control the system using traffic lights for every entering lane. We can have a feedback from here to the traffic lights to control the inflow. And the goal of the feedback should be to have here these optimal number of vehicles. In this case, it turns out to be 20. So the feedback controller will strive in closed loop to maintain here about 20 vehicles. And these 20 vehicles then produce the maximum. So you see it here in the simulation. You see that we have traffic lights here, green, red, that are changing not like urban traffic lights, but just for 1 or 2 vehicles to cross. And this increases strongly the throughput, 15% as mentioned, and so the queuing here is much less than it was previously. And the same thing can be done at work zones. So if this is the work zone, we go from 3 to 2 lanes, then if you can apply traffic lights upstream and use measurements from the merge area, you can again, in the same way, here's the no control case. So in the no control case, the inflow is higher than the capacity downstream. And as you see, you have a congestion being created. This is the no control case. And the congestion will increase, of course, depending on the arriving demand. While in the control case, you have here traffic lights. So you are measuring the density in the merge area, feeding it back, and whenever needed, you will have here, you will see here again traffic lights separate for each lane that reduce the inflow. So if there is any stochastic breakdown here, it will reduce the congestion. It will reduce the congestion, and it will maximize the throughput. And the same thing can be done, that was a German project, with variable speed limits. So you have here again a lane drop from four to 3 lanes this time. You can measure the traffic conditions in the merge area or upstream of the merge area, and you are now operating a variable speed limit which will control the traffic so that no congestion appears in this area. And we can see a video of that as well. Actually, in this video, we have the control case here and the no control case here. The merge is at the right-hand side of both. And here is the variable speed limit indication for the variable speed limit here, which controls the flow. So at the beginning, the demand is not very high, so you don't need any control. It shows 100. But if we advance in time, in both cases, you see it is already 80. Here in the no control case, we have already congestion, which creates capacity drop, and so it increases. While here, every time you have a dense traffic like now, you see the speed limit going back, 70 right now, goes to 60 also, or to 50. To dissolve the congestion in a feedback operation, you will see it here also being dissolved. Now it is 60, so that it doesn't really stay here and doesn't affect the outflow. So it's already 50 now. And as you see, the temporary small congestion can be resolved thanks to the feedback, while in the no control case, there is no such mechanism and the congestion increases. And if we go farther in time, you see here, again, no congestion. Any small congestion is dissolved by the feedback, while in the no control case, we have a strong congestion. Okay, so this means that with variable speed limits, we can do a lot of things, even if we have merging motorways and we don't want to apply traffic lights on the mainstream, we can do it with variable speed limits on the one merging motorway or on the other, or even on both. In this case, we have an extra degree of freedom that we may use to for example, do an additional task, for example, balancing the delays on both sides due to holding back. And same if you have a mainstream and a non-ramp. There are even more elaborate case studies for real networks. Unfortunately, I don't have the time to go through it. You can, of course, anytime also email me with asking for additional information. either for things that I have already explained or for things that I did not have the time to explain in detail. So let me say just a few words about route information and guidance. The point is that today we have expressway, freeway networks that are quite complex. Here again, the situation around Paris. So if you arrive at Charles de Gaulle Airport here and you want to go to this location, as you can see, you have many different alternatives. Of course, there are signs, fixed signs in this network, but particularly during peak periods and due to accidents, there may be a lot of congestion. And even if commuters know about the congested conditions, there may be a lot of accidents that are unpredictable and can, even for commuters, can present challenges regarding the route choice. So the problem is how to operate variable method signs that have been installed in order to facilitate a better exploitation of the available infrastructure. And here we have essentially two kinds of actuators. The first is about informing the drivers about the traffic conditions. The second is about guiding them according to their destination. And each of them have advantages and disadvantages, but essentially the most potentially efficient is route guidance, and the most challenging, of course, also regarding the control strategy to be designed. There are many examples of such systems. We don't want to go through all of it and different kinds of displays. And there are several very interesting issues here regarding modeling. How do we model the route choice of drivers? Regarding control, are we using towards minimizing the total travel time of all vehicles? Or do we care about having equal travel times on different routes connecting an origin and destination? In the first case, we are talking about system optimum, when you optimize the total travel time. In the second time, we talk about user optimum, when you guarantee that you never guide drivers towards longer routes than others. Even for information systems, there are interesting questions regarding how do you calculate travel times. If you take just what you can deduce from sensors, then we have the instantaneous travel time. But this may be different than the travel time that the drivers will experience on their way, because as they drive, as they travel, the traffic conditions keep changing. So whatever you thought will be when they entered the system may be different at the time they are on the system at different parts of it. There are also different approaches in terms of algorithms, of methodologies like feedback versus predictive feedback versus iterative control. And also AMOC can be extended to consider route guidance as well in the system optimum sense. Okay, these were two case studies, one for a city, which is Aalborg, and another for a whole area, which is Scotland. The difference is that in the city, you have small distances, so you can apply feedback control, while in a bigger network like the whole of Scotland, so you have Perth here, Edinburgh, Glasgow, you have a triangle of 100 kilometers for each side. And here you have really long travel times, and it is not possible to work based on feedback, because whatever you do based on information now may be quite different when these vehicles will reach specific locations in the network. So you do need some prediction for this kind of systems. Another interesting subject is the future. So in the future, as you know, vehicles are going to change. In the current system, the process is the traffic flow. The sensors are spot sensors in the system. Communications are wired. Computing architecture is usually hierarchical, and the actuators are roadside. That means everybody, all drivers look at the same signals. But with changes that we expect and are partly already there in the capabilities of vehicles, vehicle automation in various respects, we have different vehicle capabilities, and also we have vehicle connectivity, meaning that vehicles may be talking to each other and may also be talking to the infrastructure in a wireless mode. And this leads to quite substantial changes in the whole process and in the whole control loop. Specifically, the process, again, is of course the flow of vehicles, but now the flow of vehicles with enhanced capabilities. Sensors. Again, if the vehicles are connected, then they can measure various things. They know their own speeds and they can measure various things, and they can become moving sensors, submitting the information they gather. Communications, not only is going to be wireless, but you have many new communication channels. Vehicles can talk to each other, vehicles can talk to the infrastructure. So you can use these channels to do things better. And these channels were not there, are not there in conventional traffic. Computing architecture. Well, what we have in case of automated vehicles and communicating vehicles is thousands of computers, essentially, interconnected. And so a lot of things can be done within the vehicles rather than being done in the traffic control center. And last not least, if vehicles are connected, you can talk to them. So you can give different control instructions to different kinds or classes of vehicles. You don't have just the roadside actuators, the traffic lights, the variable speed limits, and so on. You can do things also individually for each vehicle. And this opens up really some new opportunities of traffic management, of influencing traffic compared to today. Okay, I will not go into highlight different problems in this context. Let me just mention the issue of functional and physical architecture. In conventional traffic, usually this is the architecture we have. We have the traffic network. We have roadside controllers at parts of the network, and then we have a traffic control center that coordinates everything. Now, if we have connected and automated vehicles, what is the possible architecture? Some people think that we may eventually go for a completely decentralized vehicle embedded traffic control, traffic management. Like, for example, as you know, happens in nature. You may have bird flocks or fish schools where there is no central controller, no coordinator, no leader, and the emerging behavior of the whole flock or the whole school is determined by the individual behaviors of its particles, of its members, of the individual fish or birds. And this is possible. However, of course, it's not obvious at all how this can happen in traffic. We may increase and have the extent of sensing of every vehicle via connectivity and have, again, a decentralized vehicle-embedded traffic management, but relying not only on the sensors of each vehicle, but also communication. Still, it may be hard to develop such systems. So we may end up again with a hierarchical traffic management, where some things are done at vehicle level, some things are done at V2V level, and some things are done at the infrastructure level, at traffic control level. And what is the exact sharing of these tasks is something that currently is investigated by many control groups around the globe. So, my last slide, conclusions. Motorway traffic flow can be substantially improved, even as much as 50% reduction of travel times at peak period and specific locations. Unfortunately, what is being used currently in the field is not always, is very often not the best possible. So we may talk about technological giants with a baby brain for many traffic control centers. Of course, some blame is also for us, researchers. Sometimes we are developing what we could call methodological zombies. That means methods that are good for writing papers, but are questionable when operating in a real world. So, but I'm always emphasizing my students, there is nothing more practical than a good theory. So a good theory does not mean necessarily complexity or I don't know what. A good theory is usually simplifying things and rendering them more practical. And in fact, we should go for as simple as possible and as complex as necessary. Also, when we design things, we need to look at general applicability, not just solving a problem in our backyard, but developing a method that can be applied at many different circumstances and locations. And also, given the last emerging developments with the vehicles, traffic control continues to be vital. Automated vehicles will not solve the traffic problems. They may even worsen the traffic problems, but they present new opportunities for better enhanced traffic management. I'm sorry that I was not very good with the time, and so, it's already 4:30. I would be glad to receive questions if there are any.
Thanks, Markos, for your talk. That was really a nice talk and comprehensive lecture over the control of traffic flow. I think we're over with the time, unfortunately, and we have a really limited time, and we haven't enough time to cover everything. But I think the next talk will start at 5, so maybe we have a couple of more minutes if there is some question. So if somebody has a question, they can write in the chat and then I can unmute them or I can read their questions. Okay, maybe, I mean, I can ask a question until maybe the others will come with some questions. I mean, my question is about the application of variable speed limit. And So what should be the characteristic of a network and like the, let's say, a congestion part when we can really apply the variable speed limit? Because for applying that, I've tried a little bit with the simulation, and there are some circumstances that we need to have, for example, like some lens available to apply this variable speed limit, and then it also I think has some relation with that. Okay, how like big is the bottleneck, and then okay, how much we can really release the speed, decrease the speed, and where the like off ramp and on ramp. So I wonder if we can kind of like formulate those things all together.
Yes, I understand the question, and I agree that when you consider a specific infrastructure to look at a specific congestion or what you can do about it, there are various things that may be of importance. First of all, of course, there must be without control, there must be a congestion with a capacity drop. That is usually the case, because in case of congestion, the outflow is usually reduced. Then you should be able to apply variable speed limits that are sufficiently low. In other words, for example, here, you are losing one lane, you have a lane drop. So the arriving flow is on 4 lanes. And you need to reduce this flow with variable speed limits roughly to the flow of 3 lanes. And to do this, you need to be able to operate sufficiently low variable speed limits. This is not always possible. I mean, we don't have the time to go in the details. We may talk offline whenever you want about the details. But roughly speaking, if the level of reduction here is high, of required reduction of flow, of holding back of flow is high, then you need to also be allowed to apply accordingly low variable speed limits. And this can go down to 40, in some cases even less kilometers per hour. And of course, on a highway, authorities are not so keen to do it. So they may tell you, you're not allowed to go below 60. In that case, you will be able to retard the onset of congestion, but you may not be able to avoid it completely. So I confirm what you say, that for reasons that we don't have the time to elaborate in detail, if there is a limit in the lower variable speed limit that you are allowed to apply, then you may not be as efficient as that. You may be able to delay the onset of congestion, but not completely avoid it. But again, we can talk also on another occasion about the more details of that.
Yeah, of course. And then maybe my last question is that, do you think what is the important characteristic that we should consider modeling the variable speed limit when we want to, for example, adopt the MetaNet, or because there are like different modeling for the variable speed limit that we can apply them to adopt the MetaNet to show the effect of applying variable speed limit in the traffic situation. So what are the important characteristics that this model should have?
The model should be able to, I mean, the way we are doing it is by changing the fundamental diagram.
True.
Right? So more specifically, I didn't explain these equations. This is the fundamental diagram with the 3 parameters, and we are modifying each of the 3 parameters as an affine function of the variable speed limit value. That's the way we influence the fundamental diagram. Another way if we don't have capacity drop that is easier, is the one proposed by Andreas Hegyi from Delft in his PhD. And he considered that the original fundamental diagram is the continuous line one. And then if you have a variable speed limit, you just take a straight line with the slope equal to the variable speed limits. And then the new fundamental diagram is this straight line. And then it is followed by the old fundamental diagram. And this is also good enough as long as there is no capacity increase. And as I mentioned, I think that in today's traffic with today's vehicle technology, apparently there is, at least that's what we found in analysis of data, there is no
capacity increase by applying the variable limit.
Exactly. So even using something like that could be good enough. You probably are talking about a paper by Jose Ramon Freio, who tried to compare different such models and present the third one that is even more accurate. I'm not sure you have this paper in mind, or if you know that paper.
Yeah, I had a look at that paper.
Yes, which may be useful to even increase a little bit the accuracy or the pertinence of the way you model. But for the basic things, any of the three approaches probably would work sufficiently, maybe not be as accurate as others, but would work for the purpose of testing different things.
Thank you. Thank you a lot for your